Okay, great. So welcome back to this Wednesday class. Today's a quiz day. Let's just move on. Okay. So today we are going to start looking at section 2B, analysis of a system. So now we are going to move on to something real. Analysis of the system may start to have like a very simple system, and then later we are going to extend it to typical application is a class. Class is an important thing for this class. Usually fairly challenging problem. Suppose if I give you a class problem, yeah, it is challenging. I don't know how much time you are spending right now to do the homework. Class problem, man, maybe, I don't know, you're spending a few hours to trying to solve one problem. I don't know, it could be, out of my own experience in the past. Of course, I'm not going to spend a few hours trying to solve class. Nowadays, I can do it for a few minutes, but not a few minutes, but you have to please, invest your time, your energy, and all that. This is a somewhat short. This is probably way too short for this class, I think. So realistically speaking, if you want to be successful in this class over summer time, I think you need to spend some time every day, every single day, you're doing something. That is probably the reality. If you're not doing that, I guess your current letter grade reflects what you're doing. So please check back your current letter grade. Okay? So let's just take a look at the system here. So we are going to continue discussion about moment. Moment, of course, you can find out the moment by using vector cross product. So we are going to apply that. So analysis of a moment comes up with two things. One is a scalar, one is moment. Okay, let's be careful. If the moment is involved, you can use two methods. One is a scalar. Scalar is oftentimes you refer to it as a graphical solution. Graphical solution is, well, force F is here in 3D space. This is the point you want to have a moment here. You have to somehow find out, okay, what is the perpendicular distance from this point to that point in 3D space. Usually that's not easy. You have to draw a very good sketch and figure out what is the distance and all that. So oftentimes we are going to depend on vector analysis. We're going to find out the vector, position vector representing from this point to the point of application of the force and then take a cross product. If you want to have a component of that moment into this certain direction, you can take a dot product to have a projection of a component. So quite important. I expect you can do both. Okay. And moment of a couple, this is the easy one. In other words, suppose if you have a force here, okay, it's like a same and equal and opposite, same equal magnitude opposite direction. This is going to create moment. This is called couple. Okay, so we're going to look at it. Okay, equivalent system. This is actually students usually don't realize it when they take statics, but this is super important. What do you mean by that? I'm teaching aerodynamics 1. Equivalent system is always used for aerodynamics 1. If you don't understand this, you can never pass Air 1. Okay, equivalent means suppose you have a system with multiple forces and moments and could be a distributed loading applied on it. Can you find out the equivalent system represented by single resultant force and resultant moment? I have to tell you that's all about the aerodynamics. Okay, so this is the beginning. So from the professor of aerodynamics says this is super important. This is super important if you're aero track. Okay, don't miss it. Okay, people usually don't realize it, but this is important. This is the first step of aerodynamics. Okay, 2.8, 2.9, those two. Reduction of a system means you're going to simplify it. Suppose something is applied, could be like multiple forces, multiple moments. You're going to reduce it to a single resultant force, single resultant moment. Okay, applied at a single point. You need to have that. Oh, those three actually. Okay, so this is think of those as aerodynamics 0001. If you don't understand it, you have a tough time now. Let's move on. Next page. So let's just continue looking at moment. So moment, of course, can be developed by force with a certain distance, okay? Something called moment arm. In this case, let's say you want to find out the moment developed at the point O because of the presence of this force F. Obviously, if you can tell the moment arm, which is 0.5 meter, magnitude 20 Newton multiplied by 0.5 meter gives you moment magnitude developed at the point O, of course, 10 Newton meter. Now, so this is the 10 Newton meter moment, MO, okay? Now, obviously, this moment can be broken down into the directional components, such as what is the component of this moment in the direction of y called my, MOY. MOY is, of course, you can get geometrically. This is going to be this component, so 3/5 times 10, so 6 Newton meters. So this is my, moment's y direction component is 6 Newton meter. Of course, you can do that. Or alternatively, this is the force F multiplied by the moment arm measured from y coordinate. 0.3 times 20 gets you 6 Newton meter. Same thing. Do you understand that? That's what you saw at the beginning of today's class. That's the principle of moments. Okay? So moment is a vector, as you can see. As a vector, moment can be broken down into some components in certain directions, just like forces. Now, this is my personal way, but if I represent moment as a vector, I use double arrow. I'm the only one using this, but I oftentimes sort of confuse myself. Is this a force or moment? So if I represent moment, double arrow plus direction of the rotation, so right hand rule. So I'm going to do this. This is M0. Okay. So this is a textbook notation. Textbook says, oh, this is moment M0, this is rotation. But usually by looking at this rotation direction, it's kind of confusing. So I'm going to put the double arrow, put the direction around it. So this is the moment MO. So this is the direction of moment. Because if this is direction moment, you can tell which way you're rotating. Okay. So I'm going to oftentimes use double arrow. And then I think this is pretty good to avoid confusion. Okay. All right, so let's move on. So in general, if the line of action of a force F is perpendicular to any specified axis AA, let's say you can draw any axis AA. Along that axis, okay, yeah, this is AA. Along that axis, let's say you have what? If the line of action of force F is perpendicular to any, okay, so this is a line of action of a force, okay. And then if you can find out perpendicular distance, which is perpendicular, if this is D, this is going to determine the moment due to the force for that axis, okay? F times dA. Actually perpendicular to. This is product, isn't it? What do you mean by that? In general, if the line of action of force F is perpendicular to any specified axis AA, the magnitude is, yeah, okay, sorry. It's just kind of confusing. So forget about it. Let's use this figure instead. So basically what I'm saying is, okay, let's say this is the force. Okay? So this is the perpendicular distance measured from X. If it's 0.4 meters, 0.4 meters is a d. 0.4 meter times magnitude of F gets you the moment developed at x-axis. This is called MOX. Okay. If, okay, perpendicular distance measured from y, you can develop this MOY. If a perpendicular distance from z, what's the perpendicular distance for z for this moment? What is the moment in z direction? What is MOZ? Go ahead.
Be 10 meters or 10 meters.
You think so?
20 times 0.5.
20 times 0.5.
So that's perpendicular to z.
Okay, so let's see. This is z. This is f. What is the moment about z-axis? It is 0, isn't it? It is 0. This is a z-axis. You're pushing the z-axis. So zero moment in about z, right? So this is basically moment is only two direction, x and y. Okay. All right. Good. That's an interesting practice, isn't it? Okay. So, anyways, let's just move on. So, alternatively, you can use the vector analysis. Okay. So obviously, you can find out moment as a vector because moment is a vector anyways. So moment developed at the point O is, first of all, you're going to find out the position vector RA, take a cross product against the force vector. So this is it. Looks like this is a moment O. As I told you, there's no Z component, isn't it? Because it's 0. Understood? So this is only moment in x and y direction only, not in z direction. Okay, let's be careful. And obviously, my, you can take a dot product of the moment vector against j, which is a y direction unit vector. If you take a dot product for such a thing, you can determine the magnitude of moment in y direction. Now, after having that, okay, in general, the component or projection of moment MO onto an arbitrary axis AA can be given by vector cross product, dot product against the unit vector for that direction. Suppose if you say, well, okay, so this is AA, I don't know, it could be anything. If this is AA, so how much moment is developed along this axis? You're going to first find out unit vector specifying that direction, take a dot product against cross product R cross F. Because this is a moment developed at point O, projection to the A is called MA. Once you get this magnitude, you can multiply with the unit vector again to get the vector MA developed along that axis AA. Does it make sense? Okay. So once again, this is a cross product, and then if you take a dot product of cross product, you're going to replace those things with that, okay? Because this is the unit vector of Cartesian coordinate x, y, z. This is the unit vector specifying that particular direction, isn't it? So you can replace that to finish up. This is that in general, if you have multiple forces, you can develop a moment by just adding them all up, vector summation. Okay. So let's just take a look at the example problem. Do you have any question here? So obviously, two different methods to determine. One is a scalar method. The other one is a vector method. Before I forget, I hate to bring it up, but Dominique, did you check your homework, by the way, solution?
No, sorry.
You should have. I took -1 point for every single one of your homework assignment. The reason is, okay, this notation. Suppose if the vector is, sorry to publicly say those things, but since I think it's important. So this is the Cartesian vector notation of A, isn't it? I think it's not your fault, but sometimes, in some math teachers, I don't know who, use this notation, isn't it? AX, AY, AZ. This is a vector notation in engineering science, engineering mechanics, soil mechanics, other things. Mainstream engineering people use this notation. This is probably mathematical rectangular coordinate notation. I think Dominique is the one favorably using this all the time.
Yeah.
It's not wrong. Okay, don't take me wrong, but this is not wrong. Some people actually use that, especially math people, math physics type. I actually discourage you using that. It's not wrong. So every time Dominique used it, I took, okay, -1. Please stop. I did this. Okay, please stop, -1. Please stop, -1. It's just intimidating little by little from trying to discourage you kind of thing. This is not wrong, but I guess out of my own experience of 20+ years of teaching, no one uses this in engineering. So I think it's a healthy thing that you kind of adapt into the engineering notation. That's fine. So I want to kind of chat with you over Microsoft Teams later. Since if you want to fix those things and promise me not to use it, I'll give you points back. Okay. If you don't care about 1 point, you just can forget about it. But I think it's 1 point each for every homework. It's kind of heavy. That's a lot of points. Okay, so I give you points back if you basically stop using. This is not wrong, but problem is no one is using, including people in industry, in engineering field. So I think it's healthy to kind of discourage students using that. So, okay, and then this is not convenient for analysis computation, anyways. It's just the expression line. Yeah, it's an expression, but it doesn't fit nicely into your equation or calculation. That's why. Okay. So Dominique, please contact me. Teams. Okay. So let's just move on to next page, page 4. Let's just take a look at example. This is quite interesting example, okay? So this is the 3D Cartesian space X, Y, and Z. Looks like line AA is also specified. Can you see the line AA? Okay. Line AA starts from origin and then going to the direction, looks like 45 degrees on XY plane, positive. Okay. So you want to determine the moment developed by the force F about AA axis. Express the result as a Cartesian vector. That means this. That means this. This is the express your result in Cartesian vector means in engineering. This is usually it, not this notation. Okay. Okay. So what is the first step? Anybody? So this is a coordinate origin, isn't it? And then this is a point of application of this force F, isn't it? So let's just find out position vector here. Why? Because by finding it, take a cross product of it, you can determine the force possible. I mean moment. You can determine this, isn't it? So that's something I want first. I want to know the moment at the coordinate origin developed by the force F. By finding this, you want to find RA. Let's find out position vector R to begin with. What is that? So I think it's a good idea to begin with the coordinate information. This is 0, 0, 0, x, y, z, 0, and 0, and 0. What about this location? What's x? What's x? Negative 2. What is y? 3. What is z? 2. That's right. So position vector R, because of that reason, -2, -0, right? -2i. 3 -0, right? Plus 3j. 2 -0, right? So this is 2k. Do you follow that so far? So this is a position vector R. Can you construct it out of the coordinate positions? Okay. So this is a position vector. The unit is meter. Okay. So from here, let's construct next. So okay, next is I want to specify the line AA. By doing so, let's find out the unit vector. Unit vector in the direction AA. Okay. So what I want is this. U. Okay. So let's find out unit vector U in the direction of AA. Okay. How'd you do that? How'd you do that? Basically, you say RAA divided by magnitude of RAA, isn't it? This is a U. So what is RAA? Coordinate here is, what's coordinate here? X equal to 4. Y equal to 4. Z equal to 0. 4, 4, 0, isn't it? So what is the position vector AA? Anybody? 4i
4i
plus
plus
4j plus 0k. That's it. This is the position vector AA. Let's divide by the magnitude. 4 square plus 4 square plus 0 square. So this is going to be 0.707i plus 0.707j. You can say this is cosine 45 or sine 45. It's the same thing. Anyways, so this is the unit vector in the direction of line AA. Why do I need that? Well, I'm trying to do this, right? This is the position. This is the unit vector in the direction line AA. This is the moment developed by the force. I want to have a projection for this moment to the line of AA. I'm doing this. Let's just apply for it. So what is MAA? It's just a magnitude because you're going to take a U, dot product, R cross F. Result is scalar, okay? So I hope you can do this. Cross product. This is the unit vector in the direction of AA. This is 0.707. Y is 0.7070. And unit vector of our vector. So position vector minus 2i, 3j, 2k. Force. What is force? Well, force is given 30i plus 40j, 20k. There we go. So 30, 40, 20. Okay. If you do a mass, 0.707, okay, let's just do a mass first of all. Take this, multiply by that, minus that. Okay, you cannot see. So, can you see? You can't. Okay, let's just use a different color. Okay. So take this times that minus this times that. Okay, 0.707. 3 times 20 minus 2 times 40. Okay. Minus this. 0.707 once again times this color here. Take this, okay. This times that minus this times that, right? So this is minus 2 times 20 minus 2 times 30. And then z component 0 because it's 0. Right? Plus 0. Okay. So if you do your math, what do you get?
56.56.
56.56. Any confirmation, anybody? Please do your computation. Get busy. Any confirmation? Get busy. Anybody got the same result?
Yeah, I got it.
You got it. That's right. It's good. So this is magnitude. So what you want is moment developed along the axis AA. So how'd you do that? Anybody? How'd you do that? Yep. Just multiply back again with the unit vector in the direction for that. Simple deal. So basically, you got the magnitude MAA multiplied by unit vector in the direction you want. So this is 56.56 multiplied by the unit vector, which is 0.707i plus 0.707j. Result is 40i plus 40j. Newton meter. This is your conclusion. So make sure when you do your quiz, homework, and exam, box your answer. That means this is my conclusion. I can easily pick it up. Any question about this? Okay. Any question? So now homework 261 is now assigned, and this is very similar to what we did today in class. So please jump right onto it. Don't wait until last minute. Okay. Things are piling up if you wait until last minute. The next one, homework 262. This is also kind of interesting because the chain AB have a force 20 newtons lifting up this door. Of course, the moment is developed around this hinge axis. Hinge axis is x. How much moment is developed? Okay. You can do that, of course. It's just a moment developed by this force along this chain to begin with, and then projection to the axis of x. You're going to take a cross product to find that moment, take a dot product to find the projection of that moment in certain direction. Obviously, the same thing we did today. So please do those problems by yourself. You got to do it today. I mean it, okay? So next, it's a very easy subject, moment of a couple. Suppose you have a force, two forces, okay, force F and force F, and then apply in opposite direction with a distance d away from it. This pair of the force create the couple moment. This is going to create the moment. This is a couple moment. Okay, moment of a couple. So moment generated by a couple is called a couple moment. Okay. And then you can actually determine the magnitude of the moment of a couple by taking some arbitrary point O, taking a position vector RB and RA. Each one of them take a cross product RA cross F, RB cross F. One is negative, one is positive. Add them together is going to create this kind of moment. So suppose if you use this point O, arbitrary point O, let's move it to right here. So let's say you are doing this. Force is F here, force is F here, minus F. Location is point A, okay? And then if you want to do the same thing, so this is a position vector R from A to B. So, like I said, moment is RA cross minus F plus RB cross F. Now, in this particular situation, this RA is 0. So this whole thing is 0. RB is now R. Okay? So what is the result? Moment is R cross F. This is the equation you have seen before. So this is the magnitude of moment of a couple.
Why is that 0?
Because A is here. Now O is A. If you move O to A, yeah, this is OA, isn't it? This is OB. Now ROA is 0. ROB is R. Okay, that's one. So this is the magnitude, the moment of a couple. Now, graphically speaking, if it's lying on the same plane, and if you know that particular plane, and then you can determine the perpendicular distance d, this is the magnitude, of course, F times d. This is the magnitude of moment of a couple. Direction is, of course, following the right-hand rule. So this couple of moment forces create the tendency of rotating this way. So I'm going to usually represent double arrow. This is a moment of a couple M. Right-hand rule, strictly speaking. Suppose you have multiple couples. Those are free vectors. Oh, what do you mean free vectors? You can freely move to anywhere else because it's a couple. So two couples are said to be equivalent if they produce the same moment, such as, suppose you have 4 different forces acting on a body. Each one of them a couple. So this creates a moment. This creates the moment. And those two are moments. Moments can be moved and then added to create the resultant moment. So this is called equivalent. These are all equivalent. Important. It's just different expressions, but overall, you have 4 different forces acting as the two couples on a body will have the same tendency or behavior with a body which has a single resultant moment of a couple located at location P. You can determine this resultant at any arbitrary location of a body, it's called equivalent. Do you have any question? This is actually, you don't probably realize it, but aerodynamics is all about this. In other words, if you're looking at surface of a wing, okay, surface of a wing, you're going to have distribution of a pressure. If you're a pilot, you know that, do you? Top surface is usually like a low pressure side. That means all over the place you have pressure acting on it. Bottom side is usually higher pressure. So you have a distributed loading just like that. This kind of thing can be resolved into certain kind of force. And then certain kind of moment. It's equivalent. And then after that, you're going to resolve this force into perpendicular direction of incoming flow. Oh man, this almost looks like an aerodynamics class. I hate doing it, but well, you're going to see it later anyways. If you successfully pass this class, good luck for you, but this is called the lift. This is called the drag. Okay, one perpendicular, one parallel to. So if you cannot do this very basic things in statics, you can never do this in aero. You know what I'm talking about? Everything is accumulated. So suppose if you're looking at your cell phone right now doing something, good luck for your life. We're not gonna see you later, guaranteed. So please try to understand what am I trying to say here is, okay? Basic things is most important. This is the only class you can get basic things. Okay, so next page, let's just take a look at, start from very basic, then you can apply for some more complicated things later, such as pressure distribution over the wing is complicated, of course, but everything is coming down to simple, something like this. So this is simple. I wish I can give you this as a quiz and give everybody 10 out of 10. Do you think 10 out of 10 for this problem? Determine the magnitude and sense of the couple moment. Please do it now and give me answer. I can do it without calculator. What is the magnitude? What is the sense? You don't need a calculator. Give me answer right now by looking at it.
Not just be 200 newtons times 4 meters.
What's the value?
800.
Not really.
Newtons, yep.
No,
800
no, that's not right.
No.
Go back and think about what we just covered. What's the answer? Take a look at your note. What's moment of a couple? Anybody?
Would be the 200 times 6 meters.
That's right, that's right. What's the value? 1200 Newton meter. That's right. What's the sense? This way, right? Okay. Okay. Okay, everybody. Hello. Have you been listening to my lecture? That's what I've been talking about. This, F times D. D is 6 meter. F is 200 Newton. 200 times 6. That's it. Sense, just sense. Okay? Hello, this is super simple. Hello? Did you get that? Okay, good. So this is a couple.
Is this just if the two forces are equivalent?
Two forces are equal and opposite. That's called force of a couple.
Or will always be the same?
Same and opposite, with a distance away with d. Okay. If so, it's going to create the moment of a couple. That's what it is. Okay. Simple, isn't it? And of course, this is the moment of a couple. Suppose if you move around this, let's say force is here and here, what is the moment of a couple? Suppose if I move it, all of a sudden this is 200 Newton, this is 200 Newton, everything shifted, but still the distance away is 6 meters. What is the moment of a couple created by those two forces? Same. Suppose if the force is here, force is there. Still the same 6 meter distance. What is the moment of a couple? Is it going to make a different moment? No, it's always the same moment. That's why this is a free vector. Okay. You can move around anywhere. You can still create the same amount of moment. That's why you can freely moving around this kind of thing. Okay. What is a good example actually? This is a good example. A twist of a 4 Newton meter is applied to the handle of the screwdriver. Resolve this couple moment. This is a couple moment because you're going to kind of twist it. Actually, this is the origin of a torque. You're going to create the torque by applying couple forces. Okay. The torque is a free moment. In other words, if the torque is here is 200 horsepower torque. I don't know. It's a power, but torque is a free moment. Okay. So if you apply equal and opposite force with the perpendicular distance away, it is going to create the torque. So this is the torque of a screwdriver, 4 Newton meter. So resolve this couple moment into a pair of couple forces. Well, yeah, that's right. So suppose if this is 4 Newton meter, what is the force here? Oh, you can solve it right here, right now. What is it? Go ahead and do it now. What is the force here? Go ahead and do it now. Everybody, pick up your calculator, do it now.
1,000.
1,000. F is 1,000.
333.
333. What's the unit? Newton. Oh. Any confirmation? Why did you get that? Divided by
the distance.
30 millimeters. 30 millimeters is what? 0.03 meter. Is going to be 4. Is that right?
So I'm just a little confused. You don't need to convert the millimeters to meters to match.
Yeah, let's convert millimeter. Okay. So 30 millimeter is 30 times 10 to minus 3 meter. So let's begin from here. Millimeter is not standard. Meter is standard. Good idea. So this is the D. So F equal to no, FD is M. M equal to FD, which is 4 Newton meter. Force is how much force? If the D is 30 times 10 to minus 3 meter.
133.
133. So okay, so this is wrong. 133 Newton. Is that what you got? Is that what you got? Yeah. Okay, you're done with this homework. Any question?
It also asks for the and P exerted on the blade.
Yeah. So
would the 4 Newton meters still be the same?
Do you think P? Do you think P is still 4 Newton meter?
I would say yes.
No, P is a force. Sorry.
Like the
No. Moment is yes.
Moment
is, but P is not.
Okay. So
obviously, distance is smaller.
Different
So P
size.
is higher, right? isn't it? Okay. So what's P? So then what's P?
That would be 4 divided by.
What's P?
800 Newton meters.
800. Anybody else? Confirm.
Yeah.
So this is the mechanism of screwdriver. How's that? You only have a hand to twist. You can only create 133 newtons, but using screwdriver, you can apply 800 newtons of force applied to a disc screw. It's a couple moment. Okay. So suppose if you use like a huge diameter screwdriver, it's going to be even better, isn't it? You can easily twist. If your screwdriver is small, thin thing, you have to really twist it. But anyways, so this is a couple moment. Here we go. Great. So let's take a look at next page, class example 272. So this is a one step toward actual application for airplane. The main beam along the wing of an airplane is swept back at an angle of 25 degrees. From road calculations, it is determined that the beam is subjected to couple moments, mx17 kip foot. What's kip, by the way? Weird unit, isn't it? Kip is probably the weirdest unit I've ever seen in this country. When I first saw it, I disgusted, but people use it, so why not, kind of thing. This is 1,000 pounds. Pound force. Kilopound. I was like, what the? Anyways, kilopounds. What kind of unit is that? I thought. Because kilo belongs to SI. Okay. Right. But people use that.
Why can't we just say half ton?
Half ton. Well, no, not the ton is the SI unit.
Ton is 2,000 pounds, so we just say half ton.
Yeah, you can say that. It's like good. Yeah. I again, as a Japanese, I hate this. I'm a U.S. citizen, but I'm Japanese. So this is 1,000 pounds, kilopounds. So kip foot. So this is 17,000 pound foot. So 17 kip foot is 17,000 pound foot. Okay. So again, it's a large number. People try to make it shorter description, which is not really good. I don't like it, but anyway. So moment is given mx and my. The coordinate system x and y is given here. But because this wing is swept 25 degrees, you're going to determine actually x prime and y prime coordinate also. So coordinate is kind of rotated in a certain direction with a 25 degrees. Determine the resultant couple moments created about x prime and y prime axis. The axes are all right in the same horizontal plane, which is good. So we're dealing with still 2D thing. So I'm going to, first of all, let me try to sketch that. So this is a wing. Great thing about it is everything is lying on XY plane anyways. So first of all, I'm going to draw a X and Y. So this is Y and X. Okay. And then this thing is rotated in a certain degree. So it looks like this is Y prime and X prime. And then angle here is 25 degrees. Yeah. So the couple moment is a vector. So it is going to be developed in X and Y direction. So I'm going to basically my own double arrow notation with right hand rule. This is mx. And I'm also going to use double arrow. So right hand notation, this is my. Okay. So you can basically dissolve this into y prime direction. Okay. And x prime direction. We're going to resolve those into two directions, obviously. This and that. Okay. So question, what's this and what's that? What's this? What's this?
Would it be
Yeah.
my sine of?
This is
25?
my.
Oh, cosine.
Cosine 25. This is
My sine.
my sine 25. Did you get that? And of course, this one can be resolved into two as well. This and that. Just slightly change the color here. The other colors. Okay. So obviously this and that. This is mx what? Mx sine 25. Okay. This is mx cosine 25. Okay. So it looks like two couple moment resolved into x prime and y prime direction. Okay. So resultant of x component is x component of this, which is positive mx cosine 25. This is negative, so negative my sine 25, which is mx is 17, isn't it? Yeah. 17 cubic foot. Cosine 25 minus my is 25 cubic foot. Sine 25. What's the body? And also resultant in y direction, y prime direction is mx sine 20, mx sine 25 positive, mx sine 25. And also positive, isn't it? Also positive, my cosine 25. In which 17 cubic foot sine 25 plus 25 cubic foot cosine 25. What's the base?
I got 4.84 and 29.8.
4 point, okay. 4 point?
Yeah.
Isn't that 40 something?
I like 4.84.
4 point?
I got 4.84 as well.
Same.
4.8? I got 48.4. Isn't that right? Something's wrong.
Did you do it with pounds feet?
Keep foot. Yeah, because this is 17.
I think you swapped MX and MY.
Mm.
So I think MX is 25, I think MY is 17. I'm just right around now.
Wait, MX is what? MX 17, MY is 25. This is, wait a minute. So this MX is, this is 17 cubic foot. Yeah, that's correct. Cubic foot. MY, this is 25 cubic foot. Anyway, I might be wrong. So what's your body? 4.84 cubic foot. I might be wrong. I don't know. So what is MRY?
29.84.
29.8 what?
4.
84. This is what I got. The same body. I got 48. I don't know why. I need to double check. Okay. So this is probably right. I'm wrong, maybe. Any question? Okay, good. So if you look at next page, so obviously this is the two forces. Looks like in vector-wise, this is opposing each other. One is positive, one is negative. Of course, the point of being here is what is the perpendicular distance, d? Okay, so this is going to create a couple moment. What kind of moment in 3D space you can create? Obviously, you need to go back to the note, basically saying, this is what the couple moment, you're going to do this, okay? And then the resultant is a moment vector, okay? So that's the homework. And then homework 273, the gear reducer is subjected to the 4 couple moments. Determine the magnitude of the resultant and its coordinate direction angles. Do you remember that? Coordinate direction angle of the resultant moment. So moment is a vector. The direction has a 3-directional angle cosines, alpha, beta, gamma. So basically the same thing. You can apply the same direction cosine equation as you did in the force, because moment is a moment. Force could be a moment. Moment is also a vector. Force is also a vector. So you can determine the direction of the resultant moment. So important thing is to put them in direction cosines. Moment. Moment is a force anyways, just like a force. So you can do the same thing, okay? All right. So next page, let's just take a look at the equivalent system. This is super important, like I said. The equivalent system is you're going to construct an equivalent system, which is essentially a body under a certain force and moment. Resultant is going to be computed and then replaced with the original force and moment applied, and then you can call that its equivalent. In other words, you can actually put the equal sign. So this is some kind of arbitrary body. This is point O, point A. Point A, you apply the force F into a certain direction. So this is the original configuration. Okay. Now you can actually move the force F to point O, right? And it's equivalent. This body behaves the exact same way. Come to think about, in order to do such a thing, in order to cancel force F applied in point A, you're going to apply negative force F at point O, then shift this force F to point O. Those two forces cancel out. As a result, force F applied at the point O. So if you apply force at point A, or if you apply the force at point O, as a body, it behaves the exact same way. This is equivalent system. It's quite important for the airplane wing analysis, of course. Suppose if you apply the lift force here, can I shift it here? Do you think the airplane behaves in the same way? Well, because it's equivalent system. Can you freely shift the force in certain direction? This direction is okay, but how about this direction? Whoa. So those are the kind of things we have to think about. So this is the equivalent system. Basic idea is, in order to determine the equivalent system, you need to think about what kind of effects you're going to introduce by applying the force F. If you apply the force F in position A, if you shift it to position O, can I do this? Can I do that? Because it's in the same line of action. It is the same thing. In other words, if you drag a, I don't know, can I push this back by doing this or doing this? Is it the same thing? Same line of action. I can push it here or I can pull it here. Same thing. Okay, anyways, equivalent. Case 2. Suppose if the force F is applied at point A. Now, obviously, line of action of the force is this, right? So you can freely move the force F within the line of action, as you saw in case 1. But this is not the case. You're going to move this force F from A to O. O is not lined up as a line of action of the force. What happens if you do such a thing? So you're going to shift this force to point O. You apply negative force F, cancel up this force and that force. However, those two forces, F and minus F, actually leave the moment of a couple. So you have to add the moment of a couple. So by moving this force F from A to O, so now the force F is acting from O. In order to make equivalent, you have to add a moment. That actually happens in aerodynamics. Lift is applied here. If you shift it to here, what happens? You have to create the moment at the same time. Quote-unquote moment coefficient is applied if the force is applied at the quote-unquote location, which is aerodynamic center, something like that. It's coming all the way from here. Equivalent, okay? Case 3. Let's say you are holding a stick, okay? Now, force is applied to pull the stick. You can apply force here or force here. It's the same thing because it's in a lined up with the same line of action of the force. However, if you apply the force here and you're holding this stick, this is the distance d. That means this is equivalent to, suppose if you shift the force from here to here, forces F is applied here. You have to add a couple moment also. So this force and then couple moment pair is equivalent to the force applied at the tip. Okay? This is case 3. Oh, this is getting kind of closer to the airplane structure. Here we go. Case 1. So those are the 3 different cases we're going to take a look at it in this unit. Okay. So in general, suppose if the rigid body is subjected to a system of multiple forces, such as F1, F2 is applied here. So point O, you have a position vector R1, R2 for the point of application of each forces F1, F2, and also you have a couple moment here. You can move those forces F1, F2 to the point O. As you move it, it is going to come up with the couple moment shows up because F1, F2 are not lined up with the line of action of each forces at the point O. So as you move F1, F2 to the point O, you are going to introduce couple moment. This couple moment can be freely moved to point O. So now you ended up having two couple moments, original couple moment, force F1, F2, all applied around point O. And you can add them up, all the forces, you can add them up, all the couple moments. You come up with the resultant force and resultant moment applied at point O. This is the equivalent force moment system. So this is equivalent. So you have F1, this is resultant force, right? Acting at point O. MRO, this is the resultant moment acting at point O. Okay. So just about any arbitrary force and moment couple applied on a body, you can resolve into two things. Resultant force and resultant moment acting at certain location. You can actually simplify the system to analyze. Okay. Obviously, airplane wing as a subject of lots of pressures. On by the wing, pressure is different everywhere. Pressure is different everywhere. As a result, you create the rift. Essentially, what you're doing this. Okay. All right. So part B, what's that? If the force system lies in the XY plane and any couple moments are perpendicular to this plane, the equation is simplified. Oh my goodness. Equation is simplified. Resultant force of X direction is sum of all the forces in X. Resultant force in Y is sum of all the forces in Y. Couple moment is essentially, let's just add them all up. If it's 2D. So we're going to start with 2D analysis. So this is the case for 2D analysis. Replace two forces, F1 and F2, acting on a stick by an equivalent resultant force and couple moment. First of all, you're going to add them up and moving it here. And then each one of them create the moment, create the moment, create the moment, create the moment, add them up. And then you can either place all the forces and moment resulting in any location, here or here, either way. It's all equivalent. Okay. So starting from next class is what? Thursday, we are going to continue doing this reduction and simplification equivalency of the force moment system. Very, very important. We are going to finish up Unit 2B on Thursday. Okay, let's stop here today. Do you have any questions? We're going to pick up from page 16. Any questions? If not, we're going to do a quiz. It's just to stop recording.